Okay, let's look at some more examples of how to apply the second fundamental theorem of calculus. If we look at this next example, we notice that, oh, sorry for the green squiggle here. We notice that the lower bound is x and the upper bound is 5. So this one is actually in the opposite order. It's not set up for the hypothesis of the second fundamental theorem of calculus. So we have to do a tiny bit of work first. We have to just recognize this property of integrals that tells us that if we switch the order of the bounds, we can change the sign of the integral. So this is the same thing as negative the integral from 5 to x of 3t sine of t. And once we've changed it so we have a negative out front and switched the bounds, now we still start with a constant down here and an x up here, and we can apply the second fundamental theorem. So our result will be negative because of the negative out front. And then since little f of t is the function 3t sine of t, the second fundamental theorem of calculus says the result should be f of x. So that would be 3x sine of x. And we're done. So the negative out front is to switch the bounds, and then we've just got our function f of x. Notice that this one we actually could not do the long way. We are required to do the second fundamental theorem of calculus because we don't, at this point in our careers, know how to find the antiderivative of such a thing. If you take calculus 2, you might learn how to do that. But for now, we don't know how to, so we have to rely on the second fundamental theorem of calculus. Okay, now we look at this next one. This next one is different yet because now instead of just having an x up here, we have an x squared. So I'm going to do this one out using the first fundamental theorem of calculus because I want to show what's going to happen in general here. So let's take the antiderivative of cosine. So the antiderivative of cosine is sine of t, and we want to evaluate that between 1 and x squared. So what we're really doing is we're taking the derivative of sine of the upper bound, x squared, minus sine of the lower bound, 1. So when we go to take the derivative of this, chain rule is going to pop up. So chain rule is going to be key when we have some sort of function in our upper bound instead of just an x. So what's going to happen when we take the derivative of sine of a function? Well, chain rule says it's going to be cosine of that function, but then times the derivative of that inside function. So the derivative of x squared is 2x. Now, the derivative of this constant still goes to 0. So we're just left with cosine of x squared times 2x. Okay, so now what we need to do is try to think about if we could generalize, maybe let me change colors here. If we want to generalize, that's not very different in color, but generalize the second fundamental theorem of calculus. And what we could say is if we were trying to take the derivative of some integral where this was some function, so I'm going to call it like g of x, some function of x instead of just x, so something like x squared. And we still had our f of t dt. So second fundamental theorem of calculus, it feels like all we would want to do is just say it's f of g of x, right? We'd want to take this g of x and replace our t, just like before. We were replacing our x with, or replacing our t with the x, right? So we'd want to replace our t with our g of x, but chain rule would also say don't forget to also multiply by g prime of x. So this would be a sort of generalization of the second fundamental theorem of calculus that we could use if we have some function. And it's really just applying chain rule to the second fundamental theorem of calculus. Okay, so let's see how we can do that in a different example. So in this case, notice we have what's happening in both of the previous examples. We have to switch the order of the bounds so that the constant is, oops, I guess I'm still in that gray color. Oh well. So I'm going to switch the order like we did before. So my constant is down below, and I have 1 plus 3x squared on top. But now notice that this is some function in terms of x. So second fundamental theorem of calculus says my f of t is 1 over 2 plus e to the t. So I want to replace that t, f of t, I want to replace the t with the function 1 plus 3x squared. So I have my negative out front, and I have 1 over 2 plus e to the 1 plus 3x squared. So all of this is my f of g of x. And then chain rule says multiply by the derivative of the inside function. So multiply by the derivative of 1 plus 3x squared. So multiply by 6x. So there we go. So this is slightly more complicated than second fundamental theorem of calculus seemed at first. But the only difference is instead of replacing your t with x, you're replacing t with your function. And then you have to remember to multiply by the derivative of that function. Okay, so let's look at one more here. This one, notice that we have functions on both ends. So in order to have it meet the hypothesis of the second fundamental theorem of calculus, we have to use additivity property. And we're going to break this up into from x squared to some number. You can pick your favorite number here. Oh, and this should be a t here and a dt. I mean, the t is really just a dummy variable because you're going to be replacing it. But so I'm using additivity here to break this integral up so that I have a constant on one bound and a function on the other bound. And then the first one, I need to switch the order of the bounds because it has to start with a 0, again, to meet the hypothesis of the second fundamental theorem of calculus. So I can write it from the integral from 0 to negative, the integral from 0 to x squared of sine, plus from 0 to x cubed of sine. And so I've broken it up now into two pieces, and now the second fundamental theorem of calculus would apply. The derivative would just be negative. Now I take this function and I replace the t with x squared, but then multiply by the derivative of x squared, plus, let's do the second fundamental theorem again, taking the derivative of this thing. So second fundamental says replace t with the function x cubed, but then multiply by the derivative of x cubed. And there we go.